today's session. So last class we have seen the hydroelectric power stations, right? So we have seen the what are the constituents of hydroelectric power plant, like dam. Okay, how the dam is being built and how the water is being stored and how it is taken, and what are the types of the dam. Which are the suitable dams for suitable locations. Then what is spillways? Okay, so spillways. What are the uses of that spillways? We have seen, and I have shown some pictures also. I have shown some pictures also. The spillways, then and also the headworks. So I have shown some pictures also regarding this spillways and headworks. Okay, so in headworks we have seen how the water like waste, that is debris or some particles that is getting being sedimented. So how the construction be like of spillways and headworks, and I've shown some practical example of surge tank. I think, have you visited your overhead tank, how it is being connected? Like so like that we have seen what is the usage of this surge tank, and how the pressure is inside the penstock is being limited by this surge tank. We have seen. So penstock also you have seen, like so mostly we are going for concrete penstock, and sometimes steel. You know, what are the causes of using the steel? Okay, steel also that will be easily get rusted. Okay, rusted. We have to go for frequent maintenance, and we have to go for frequent replacements. Okay, once in a year, and once in a month you have to go for frequent maintenance. So that is goes your construction of the your power plant to the maximum. So now we are going to see about the turbines. What are the turbines we are going to use in this hydroelectric power plant? So if you see the turbines, there are two types of turbines. Okay, so mainly the water turbines are used to convert the energy of falling water into mechanical energy. So the principal types of water turbines are, so first one is impulse turbine, and second one is reaction turbine. Okay, so impulse turbine, if you see, okay, so this turbine are used in some high heads, okay, high heads of water. So in an impulse turbine, the entire water pressure of water is converted to the kinetic energy in the nozzle, and the velocity of jet drives the wheel. Okay, so one such example of impulse turbine is this Pelton wheel turbine. So you can see in this picture a nozzle. Okay, so this is your penstock and connected to a nozzle. Okay, so that nozzle. Why we are going for nozzle? Because to increase the pressure. Okay, to increase the pressure of the water further. Okay, so even though you can get the speed of the water, like some 80 to 90 km/h, So if you are using this nozzle, so you may able to get even 120 kilometer per hour up to 150 kilometer per hour. So I already said how the what is the speed of the water that is being hit to the that is being hit by that turbine. Okay. So here, if you see the belt and wheel turbine, it is of bucket type. Okay, so that structure is being connected with a bucket. Okay, so every time it is hitting the nozzle. So some disturbance are coming. Please mute yourself. Okay, so every time each bucket is hitting the nozzle, you will get some more power. Okay, so more power. So for that purpose only, we are going for belt and wheel turbine. Okay, recently they have I've seen one YouTube video. So in that what they are doing is in water sink. So in kitchens you will find a water sink. So in that sink also what they are doing is they are keeping a small turbine light. Okay, so whenever you are opening the water, that small turbine is there. The turbine also it's getting rotated. So by that we can generate some small amount of power. With that we can light a small LED light. Okay. Similarly here also. Okay. So imagine same turbine you are using in your wash basins. Okay. So imagine this nozzle is like your like water tap. Okay. So water tap, if you open, how much pressure it is coming. Okay. So while keeping the hand inside your water tap in the water basin, okay, so you'll get some more pressure. So even that also like hitting a turbine and small amount of power is being generated. So that is that can light up a LED. Okay, similarly here also like a belt and wheel turbine, same like a bucket type. Okay, so if one bucket moves like this, again the next bucket comes. So next bucket comes into that nozzle. So next bucket it is hitting that. So you'll get more power. Okay, so that you'll get more rotation. Okay, so it will not rotate like 1500 RPM. How it is rotating in your machine slab. Okay, so machine slab, the motor is integrated with the alternator. So the motor is running at 1500 RPM. Similarly, so meanwhile the motor also coupled with the alternator. So your generator also running okay at 1500 RPM. But not in like normal, like in practical problem, it will not rotate in 1500 RPM. Okay, so that much speed, if you want to rotate, you have to give that much pressure. Okay, so here in this belt and wheel, it can rotate up to 200 RPM. 200 RPM is the maximum speed. Maximum speed. If you go for 100 megawatt turbine, 500 megawatt turbine. So 200 RPM is the maximum rotations per minute is the maximum speed. Okay. So here, this it consists of a wheel fitted with the elliptical buckets along its periphery. Okay. The force of water jet striking the buckets on the wheel drive on the wheel, which drives the turbine. Okay. So which drives the turbine. The quantity of water jet falling on the turbine is controlled by a means of a needle or sphere. Okay. Here, after this class, I will try to show some videos. So in which you can find clearly. So this needle sphere movement like that, which is placed in the tip of the nozzle. The movement of the needle is controlled by the governor. If the load on the turbine decreases, the governor pushes the needle into the nozzle, thereby reducing the quantity of water striking the buckets. So this scenario will not happen. Why? Because due to the ever increase in the power demand, so there is no reduction in the power generation. Okay, there is no scenario like we have to reduce the generation. So that is particularly in the winter season you can expect. So that too, they will not reduce the speed or reduce the generation. They will simply off say for example, there is a series of generator. like one is 100 into 500 megawatt. So simply they will off 200 megawatt, 300 megawatt based on the sudden okay, drop in the demand. So they will not go for this needle movement, and they will not okay, try to reduce the efficiency of the generator. Like if you they try to reduce the efficiency, so even though if you are generating, there is no use of running that uh, alternator, that is turbine. Alternator is coupled to the turbine, no? So there is no use when the efficiency drops very less. So by that time they will simply stop the turbine. They will go for some other base loads, example thermal loads, like nuclear loads. So the reverse actions takes place if the load on the turbine increases. So next is a reaction turbine. So two types of turbine: reaction turbine. So reaction turbine was used for low and medium heads. This impulse turbine is used for high heads. Okay, this you have to keep in your mind. So there are two types of turbines which is used in the hydroelectric power station. The first one is impulse turbine, and the second one is reaction turbine. So reaction turbine are used for low and medium heads. So in like southern part of India, most of the dams are like medium heads. Okay, medium heads are low heads, as I said. So due to the depends on the climatic condition. If it rains, our dams will fill, or otherwise it won't fill. Whereas in northern India, the scenario is just opposite of southern India. So northern region, you will get more water in the dams. So like Ganges rivers is there, here Brahmaputra river is there. So even yearly, out of 365 days, you'll get 350 days full of water. Okay, so 24/7 you're getting the water. So dam is filling like anything. So the generation from the hydro is more. Whereas in southern India, so still in if you take like in Telangana region, we want to okay, we are just looking for the rain. Okay, so in summer season, before the starting of summer season, there will be some heavy rain. So we are still looking for the rain. So if it is rains, our dam will get filled up, and we can go for generation with the like hydro power station. Even we are generating, but a little bit amount. So if it rains heavily, so we can really we can reduce some cost on thermal power station. So entirely medium heads or low heads. So in reaction turbine, water enters the runner partly with the pressure energy and partly with velocity head. Okay, so water enter the runner partly with pressure energy and partly with velocity head. The important types of reaction turbine are Francis turbine and Kaplan turbine. A Francis turbine is used for low to medium head. It consists of outer ring of stationary guide blades fixed to the turbine, chasing an inner ring of rotating blades forming the runner. The guide blades control the flow of water to the turbine. Water flows radially inwards and changes to a downward direction while passing through the runner. Okay, so water enters radially inward and changes towards the downward direction. It will be like, so hitting the turbine like this. So after that, the water okay, flows to the downward direction also. I will show the video so that you can clearly understand. Don't worry. So while passing to the runner, as water passes over the rotating turbine of the runner, both pressure and velocity of water are reduced. Okay, so when the water passes over the rotating blades like this runner, so the rotating blades, it will be like this. Okay, so if you see the turbine, so imagine this is a turbine. It will be of some rotating blades. So water is sitting the rotating turbine initially here, and even it is also going to the downward part also. So this kind of Francis turbine. So here, this causes the reaction force which drives the turbine. A Kaplan turbine is used for low heads and large quantities of water. Okay, low head and large quantities of water. It is similar to Francis turbine, except the runner of Kaplan turbine receives the water axially. Okay, so water flows radially inwards through regulating gates all around the sides, changing the direction in the runner to axial flow. This causes the reaction force which drives the turbine. So next, after that, the electrical equipment. Okay, so this is up to the turbines. Next is the electrical equipment. So after that, after the alternator, so turbine is hitting the alternator. So alternator, so we are having after that electrical equipment like alternator, transformers, circuit breakers, and other switching operations and protection devices. After alternator, so as I said, so the alternator sizes of from 11 kilovolt to 25 kilovolt. It depends on the size of the generating station. And we are what they are doing is we are going for step-up transformer. Step-up transformer like this 11 kV or 25 kilovolt is being stepped up to the 400 kilovolt or 765 kilovolt. Okay, or 100 kilovolt, 100, 200, 1200 kilovolt. Like that, we are stepping up the voltage and we are sending that voltage towards the very long distance. Very long distance like 300 kilometers, 400 kilometers. We are transmitting that power through the transmission lines. And after that, circuit breakers. So protection, some isolators will be there. So for isolating, and in between switching substations will be there. Switching substations means like 400 bar 220 kilovolt substation, 400 bar 320 kilovolt substation. So 400 bar 220 volt. So next is it is traveling to some 200 kilometers. So there you will be finding some switching substation that is of 400 kilovolt bar 320 kilovolt or 400 kilovolt per 220 kilovolt. So after 220 kilovolt is further traveled to some other distance, say 200 kilometers. So that 220 kilovolt is further being stepped down into 110 kilovolt. So 110 kilovolt again being stepped down into 66 kilovolt. So 66 kilovolt is again being stepped down into 33 kilovolt. So 33 again to 11 kilovolt. So that's where you will be finding nearby your substation ratings of 33 bar 11 kilovolt. 33 is the incoming feeder. You are getting the 33 kilovolt supply. Outgoing is 11 kilovolt. So 33 bar 11 kilovolt. So again, that 11 kilovolt is being transmitted over some kilometers, say 5 kilometers, 6 kilometers like. So for the, such areas which that substation is being connected. So you will be finding that pole mounted transformer. Pole mounted transformer, what is the rating? Have you found out the rating of the pole mounted transformer? So pole mounted transformer, if you go nearby the to the pole mounted transformer, if you see the nameplate details of the pole mounted transformer, so you will be finding like 11 kV bar 415 kilo. 11 kV bar 415 kilovolt transformer. So that 415 kilovolt, from that 415 kilovolt nearby your streets, you'll be finding more this kind of pole mounted transformer. So 2 or 3 streets once you will be finding a pole mounted transformer that is of that rating, that is 11 kV bar 415. So from that 415 volts, so we are taking for 3-phase supply. Those who want 3-phase supply, so we are taking. So 3 wires and 1 neutral. So those who want single phase supply, 1 phase and 1 neutral, 2 wires. 2 wires, one line is for stay wire. So single phase also you will be finding 3 wires. So 1 for stay wire, next to 2 for your that is phase and as well as your neutral. So the three phase, if you go for three phase, that neutral wire is itself acting as a stay wire. Neutral wire is acting as a stay wire, and you will be finding three wires. So three supply RYB supply. So those who are using three phase supply, so you will be finding in your that panel board. So you'll be having your energy meter. There will be some three phases. In some other meters, okay, so that will be not given by your electricity board. So you have to install a separate meters for, so which phase is on. Say for example, RYB three phases are, so which phase is on during the particular time. We will be taking one phase through some two rooms, one phase to some two ACs, so one phase to some other rooms, like that. So if your AC is in on, so you can go to nearby the meters, you can find so which phases are taking more supply, like that. Also you can easily find out nowadays due to the modern electronic meters. So, and also circuit breakers you will be finding in substation. Okay, so for easily isolation from the faults, protective devices. I think you are studying your protection and switchgear and your measurements and instrumentation subjects. This circuit breaker, okay, protective devices. So next we'll move on to the So now I am going to show something on your structure of power system, because still you are in some confusion. So now we are going to I'm going to show you the structure of power system. Structure of power system. So if you see the historical development of electrical power system, so this electricity was invented in very earlier age, but not so become commercial usage. It is began in late 1876. 1870s itself, it is a little bit coming to the commercial, when arc lamps was used for lighthouse illumination and street light. So that time the credit goes for inventing electrical power goes to our Thomas Alva Edison. Okay, so Thomas Edison only has established an electric power station at like historic Pearl Station, that is located in New York in 1881. So this is the first commercial power plant coming to the operation. So but even though it was started in 1881, but operation was did in 1882 September only. Okay, so this station has capacity of 25 HP boilers supplying steam to 6 electric dynamo sets, that is DC generators. Only DC supply they are being supplied, and supplied to the power of 59 customers. So this is the first commercial substation, that is DC only, that is being supplied to 59 customers. So roughly within 1.5 kilometer radius, 1.5 kilometer radius at 110 voltage to underground cable system. Okay, So in that time itself, in 1881 itself, they went for underground cable system, cable system. So there were similar developments in other cities. So later, a few years, DC motor loads also were added to such system. So after the invention of Frank Sprague in 1884. Okay, so the invention of transformers and the AC system by Gollard and J.D. Gibson of France, Paris, France, made an AC electric power system possible. The first practical AC distribution system was installed for 150 lamp loads. Okay, this is the first AC distribution system for 150 lamp loads in USA by William Stanley. Okay, at Massachusetts in 1886 for Westinghouse. Okay, so Massachusetts, okay, is the world's top university is located. That is Massachusetts Institute of Technology, MIT. Okay, so in 1886 for Westinghouse. So he also acquired American rights to the transformers. So thereby the development of polyphase, that is 3-phase by Tesla. So Tesla only have developed this the polyphase system. So this increased the attraction of AC systems, and by 1888, Tesla's hold several patents on this AC motors, generators, transformers, and the transmission system. And then Westinghouse bought the patents of early inventions. In the 1889, the first AC transmission lines. Okay, the first AC transmission line at 4,000 voltage, only single phase. Here, only single phase. So 21 kilometers was put into operation in Oregon, North America. Okay, between this Willamette Falls and Portland. In 1890s, there was a great controversy over whether power utilized should be standardized on AC or DC. So which we have to rely on, whether we have to go for AC or DC. Okay, so in 1890s, so there was very huge great controversies over this, whether we have to adapt the AC system or DC system. So Westinghouse advocated AC and the Edison favored for DC. So finally, AC won out over DC. So due to its various advantages, I think you already studied, okay, such as voltage transformation. Voltage transformation is easy because transformer is there. Okay, so transformer, you can easily transfer one form of voltage into another form of voltage without changing the frequency. Okay, so even 25 kilovolt can be step up into 1000 kilovolts. Okay, 1000 kilovolt or 1200 kilovolts with the help of transformer. Over without changing the frequency for a very large distance. That is possible, but whereas in DC, so DC transformer won't works in a DC system. Okay, so DC system, so you have to generate a very huge amount of power for transmitting over DC. But whereas in AC, you can't. So transformer is there. So no need to worry about the more power transmission. There is you have to go for very huge generators for DC. Then so let's so some compact. When compared to DC, compact generator is enough for generating ACs. So that is the main advantages. So for AC power that is being transmitted over a long distance. Okay, long distance, and also control also very, very simple, economical utilization, like control and all we are going to see the further classes. Okay, so in 1893, the first three-phase line in southern California, that is in North America. Okay, came into the operation of 2.3 kilovolt. 2.3 kilovolt. This is the first three-phase line in 1893. In 1893. So first 1890s only. Okay. So 1889 first they transmitted. So that is the starting of AC power. Okay, 1889. That is of 4,000 volts. That is a 4 kilovolt. So after that, in 1890, after 4 years, okay, after 4 years, they went for three-phase line. First three-phase line in Southern California. Okay, Southern California. So that is of 2.3 kilovolt. 2.3 kilovolt, which was 12 kilometer long. Okay, so this is of 12 kilometer long. So there was phenomenal growth of electrical power thereafter. After 1893 only, so they tested 2.3 kilovolt. So after that only, so phenomenal growth. Okay, slowly that is being voltage is being raised, and due to the modern innovations of alternator and okay, transformers. So we went to some more lines. We have installed more transmission lines. Okay, then distribution system be okay, expanded. So after that, you know how it is being okay, developed. That's the development and all. You know. So next we are going for operating voltages and operating frequencies. So initially the frequencies were not same like 50 hertz or 60 hertz. So initially they were using like 25 okay, hertz, 50 hertz, 60 hertz, 66, 125, 133 hertz. Okay, so like this many hertz frequency they have tested initially. So which created many difficulties in the interconnections, everything, and therefore for standardization of frequencies was felt necessary. So in Northern America, they are adopted 60 hertz. However, in many countries, okay, they have adopted 50 hertz. In Northern American region, they have adopted 60 hertz, and some countries they are using 50 hertz. So we are falling under 50 hertz. 50 hertz. So we are falling under 230 volt 50 hertz single phase, or 440 volts 50 hertz three phase. Okay, three phase. So while writing itself, you have to write like 230 volt 50 hertz single phase AC supply. Okay, 440 volt 50 hertz three phase AC supply. Okay, like that. So in foreign countries, some other foreign countries, they are adopting 60 hertz 110 volts, 60 hertz 230 volts. Like that they are adapting. So majority they are following 110 volts, 60 hertz. So that's why you are finding in your iPhone adapter. So you'll be that adapter can work in 110 volt, 60 hertz also, and there is two modes are there. Automatically it will turn on to your mode. So even if you are taking your iPhone charger to US, you can use same charger in India also. You can in 230 volts 50 hertz also it can work, and 110 volts 60 also it can work. So up to 1921 AC system voltage were used. AC system voltage like 12 kilovolt, okay, 44 kilovolt, 60 kilovolt RMS line to line voltage it is used. So which further it is increased to 165 kilovolt in 1922, and 220 kilovolt in 1923, and 287 in 1935, 330 kilovolt in 1953, 500 kilovolt in 1965, 735 kilovolt in 1966, 765 kilovolt in 69, and 100 okay, 1100 kilovolt, 1100 kilovolt in 1990s. it was felt necessary to standardize the voltage system. So in that scenario, they decided. So entire in the world countries, they have decided to standardize some voltage, common voltage. You that standardizing voltage. Okay, transmission of voltage. That the entire thing you will be studying in detail in next part. That is power systems 2. This part only we are concentrating on and distribution. Generation and distribution. We'll discuss something about transmission also. But the entire transmission part you'll be studying in the next part. So if you see, like every country has different standard rating. In India, 132 kilovolt, 220 kilovolt for a high voltage, and a 400 kilovolt, and 765 kilovolt for extra high voltage. In some other countries, this is not extra high voltage. In India, only 765 kilovolt is extra high voltage. In some other countries, in foreign countries, this 765 kilovolt is still high voltage. And although 765 kilovolt has been constructed in India, so this is old topic. Now 765 kilovolt is in existence, and even 1000 kilovolt also they have tested, commissioning, everything tested. And earlier development witnessed the different generating voltage and unit size, and the generating unit size up to 1300 megawatt, which was made operational in 1973 in Tennessee Valley Authority. The maximum generating voltage advanced countries are 33 kilowatt. In India, now it has reached up to 25 kilowatt, and highest unit size is 1000 megawatt nowadays. The growth size of unit sizes were possible only after interconnection and better cooling system. So interconnection, I said, interconnection grid formation, everything was did in India. So everything is connected with the grid system. Okay, even from Kashmir to Kanyakumari, it is connected with the grid, entire one grid. After the formation of one grid in 2010, after 2010, after they formed the one grid, one nation. Okay, well, 2012, actually slowly they started from 2010 onwards. 2012 only, 12 and 13, 14 only, the entire thing was completed. Okay, still they needed 4 years to integrate entire India. So now whatever the generation is being integrated in the one part, it can easily reach us the another part also. So it depends on the state shares, okay, interstate shares, everything that detailedly discussed in the class. Okay, so now we can move on to the. So this is how like HVDC. So if you see like HV, high voltage DC transmission system. I think this high voltage DC transmission system we are going to study the whole subject in the next year, third year, separately. The whole subject you are going to study. So how what is the technology behind high voltage DC transmission system? So which was started in 1954 when Swedish power board was started. So they energized 60 mile 100 kilovolt DC submarine cable system from the Gotland and Swedish mainland. So with the advent of mercury valves in early 1950s, HVDC transmission became very economical for long distance transmission. The development of new solid state technologies, like after the 1950s, HVDC has become more attractive So today, numerous installation with standard voltage reached up to 800 kilovolts. So this they went for 1200 also, 1200 kilovolt also now, and have become operation in the world. The DC transmission may advantages over AC transmission for more than 500 kilometers for overhead line. So if you take like a DC transmission system for more than 500 kilometers. So only you see in DC system only two lines is passed, only positive and negative. Okay, so in AC system, if you see like in the transmission system, you see like three phases, and in one transmission tower itself, two circuits are. Okay, so parallelly we are taking two circuits for reducing the line cost. Okay, so two circuits, sometimes three circuits in the one transmission line itself. Okay, so if you see like more than 500 kilometers, this HVDC system had more advantages when compared to the HVAC system. In India, like this is old data. This has been increased now. 500 kilovolt the transmission system from Rihan and Dari. Now it has been increased. Next, in 1998. So 1998, after a high voltage synchronous machine called power former, that is suitable for direct connection between the high voltage network without any step up transformer is launched. The first power former was 45 kilovolt, 42 MVA, and one turbo machine related to 136 kilovolt, okay, and one hydro machine rated at. So installed in Sweden, but even though now this concept is outdated, so generally we are generating the like 11 kilovolt and up to 25 kilovolt, and that is being transmitted over very large distance, and we are stepping down as I said to like 400 to 220, 222, 110 to 66 to 33 kilovolt, then 33 to 11 kilovolt. Like that, we are stepping down, and that we are going for taking into the operation. So this is in detail about the history of power generation, history of DC power generation, and how it is being transmitted, and what is the distance, and what is the year. So a little bit year and all you can just remember a little bit year. That will help for writing, okay, and a little bit advantages between the HVDC system and the HVAC system. So don't worry, you are going to study the entire thing detailedly in forthcoming years. So this is just like an introduction only. So in next class we'll see the structure of powers. With this, I'm going to wind up today's class.